Hello, so today I'm going to talk about our paper refuting the deterministic direct sum conjecture. And um, more specifically, I'm going to talk to you about alternating communication games, which is the construction that we use in refuting the direct sum conjecture, and also the related lower bound technique. So the alternating communication games, I think, is a special case, or so these constructions, these kind of functions were already existed in the literature, um, in the form of pointer jumping, like the pointer jumping constructions, which is a sort of more abstract or higher level way of defining these alternating communication games. But I think that um, the way we frame it and the sort of related lower bound technique allows for more fine-grained study of the properties of the construction, and actually I think is of interest in itself. And hopefully I can convey some of that in this talk. So this is joint work with Abdallah Saffidine, and I'm Simon. The the problem that we address in the paper is the direct sum problem in the setting of deterministic communication complexity. The We're interested in total functions, so this was already it was known that savings were possible for the case of partial functions. Here we're interested in total functions, and the question we're asking is, can you save more than a constant number of bits if you have L copies, if you're trying to elicit L copies of a function f in the communication complexity model? So the conjecture is that you that basically this equality is true, basically, that you have linear scaling when you um, solve the functions in parallel, and it's widely believed to be true. It If you restrict yourself to the setting where you have only two rounds of communication complexity, it holds. It also holds for some different complexity measures, and you can prove it that it holds for most known explicit functions. So why is this question significant? Well, it's through the Karashma-Raz-Wigderson program. Related sort of direct sum questions on communication complexity are linked to circuit complexity, and specifically circuit depth. So separating NC1 circuits from NC2 and by extension p-poly circuits. Um, but so the direct sum question that we're answering doesn't um, directly relate to this, so it doesn't solve that open question. Um, but it's of a similar flavor. It's a similar flavor type of question, and it's a fundamental setting in the sense that the deterministic communication complexity for total functions is probably the most basic framework for in communication complexity. It's the one that was initially introduced by Yao, and so answering whether you can sort of whether you have a direct sum theorem on in this setting is a pretty fundamental sort of theoretical computer science question, especially since direct sum questions, independent of the Kashmir-Raz Wigderson program, are fundamental in computer science, and like you you have versions of these, asking if how problems scale when you have multiple instances in parallel is a fundamental theoretical computer science question to ask. And beyond the sort of motivations of a specific problem, like I was mentioning at the beginning of the talk, the construction I think is very natural, and the way we frame it and the lower bound technique uh, that we introduce with it, basically I think is of independent interest, and I think it can be studied further, and variants can be defined, and I think those variants will prove to actually be useful in solving other problems in communication complexity. Okay, so the actual result of the paper is that we refute the direct sum conjecture in its strongest form, or maybe not its strongest form, but in a strong form of it, which is we give us show that it's basically have sub-additive behavior in the sense that you can shave off a constant from the linear term. Uh, so for some small epsilon, you basically show that like if you have L functions in parallel and with L sufficiently large, you end up with the complexity of L functions in parallel is 1 minus epsilon L of times the complexity of a single function. And the function, the specific function that we show has this property is these alternating communication games. So this is a very high level. I'm going to give you a very high level approach of idea of how we approach this. The sort of first thing that we do is we design our construction in a way that we highly constrain the possible valid protocols. Then second, we force the alternation between the two players. And third, we use the fact that the number of bits that need to be emitted by a player is an integer number at every round, and so we can build the game in such a way that some of that some of that integer number of bits is actually slightly redundant, and so there's every round some amount of communication is actually wasted in the single game, and then when you combine the games together, you can amortize that waste, or you can basically communicate them in batch so that like you don't end up wasting that bit. And the reason why that actually grows as the construction grows is because there's a fractional bit that's wasted at every round of communication. So to build the construction, we define this operator that we call the interlacing operation. So this is a formal definition, but I'll give you an example because the idea is actually fairly simple. And so if you have a matrix A, which is just a basic 1 by 2 matrix, 1, 0, so the matrix A2, which is interlacing it with itself, so twice, which we can also denote this way, what you basically do is you copy the first column of A by the number of columns of what you're interlacing it with, so in this case A again. So you have here, because there's 2 columns, you basically copy the first column twice, copy the second column twice, and then have a concatenate with a version of A below it and another version here. Now if you want to do A3, so this operation is associative, by the way. So if you want to do A3, you can basically just do interlacing A2 with A, which means that because we have 2 columns in A, you end up having you take the first column of A2, you duplicate it twice, and you append at the bottom a copy of A, and you do that with every column of A2, and so you end up with this matrix. And you can keep going. So, and you have this is A4. So the idea of this interlace operation is like very straightforward. So the construction we define is like alternating communication games. The definition is basically you start with this 1, 0 matrix, and we define it inductively. So where basically you have this phi subscript I, and to get the next round, basically I plus 1, phi I plus 1, what you do is you interlace phi I with b copies of itself, where b is a sufficiently large integer. In the paper, we think we settle at 10,000. So you have phi I interlaced 10,000 times with itself. Take the transpose, and that gives you phi I plus 1. And this is how basically we define this family of function alternating communication games. And the property that we're interested in is basically the players must speak for I rounds. So there's I rounds of alternating communication between the two players, and at every round, a fractional bit is wasted. Is the property that the construction has. So here's just a simple illustration to like here I've set b to be 3 instead of 10,000, just to actually give you a visual example. But you start, so in this graphic, you this is an array plot of a matrix. So like the dark square is 1 and the white square is 0. This is phi 0, 1. So now if you interlace it with itself, you end up with part B here, where you end up with this matrix is phi 0, 2, then phi 0, 3 here. Then I transpose it to get phi 1, 1. So this is just the next round of a alternating communication game. And then when I interlace that with itself, I end up with this matrix. And then if I interlace it 3 times, I end up with this. And so you can keep going for any number of rounds that you want. And in the real construction, instead of like transposing once we reach 3, we transpose once we reach 10,000. So the specific reason why we choose 10,000 is basically ends up being quite fiddly. So I can't really explain in a sort of easy manner why this is the case. But like if you look at through the details of a paper, you the sort of logic of why you end up needing a number beyond a certain size sort of will be clearer. But because the idea here is quite straightforward, but when you end up trying to prove the lower bound, there are some details that become slightly messy. So you have to be careful with a few things, and so unfortunately, we don't know how to prove it for for a much smaller version of a construction where you would just alternate every after interlacing 3 times and just transpose 3 times. But from an intuitive point of view, it does, like this construction, like you can see that if you look at like little f here, the way to play on this game, it seems kind of obvious that the best thing to do is for the if you have this matrix, you want the row player to separate the 3 interlaced games here, and then no matter like which part or whatever the partition we end up in, then you want the column player to start emitting bits and separate the 3 sub games in that are in the element of a partition that they're sort of given. Okay, so that's the construction, and to actually show the lower bound, the sort of central construction, or the central object that we use for the lower bound is the sets that are obtained through this what we call the bracket notation. And so it's basically I have like 4 parameters, or basically it's a notation that like if you have a matrix M and you have these brackets where you give it an integer p and 2 real numbers from 0 to 1, x and y. And the sort of the way to interpret this is we build a set S of matrices that are made up from a fraction x of rows of M. So like if x is 0.5, basically you take half the rows of M and you build a set S, which is the set of all matrices where you have half the rows of M. So um, so we take the natural extension of the interlace operation to, instead of interlacing matrices, we can interlace two sets of matrices by basically what you would naturally do, which is just get a new set, which is all possible combinations. And so if you have a set S, or where you have half of the rows of M, you interlace that set with itself P times, and then you get the set SP. And then you build a final set T that is made from submatrices formed by taking a fraction. So you take Y. So if Y is, say, a quarter, you take every matrix in SP, and you take a quarter, like all possible matrices obtained by taking a quarter of the columns of each matrix, and then you get a new set T, which has been built from all those matrices. So I'll actually go for an example to sort of maybe make the parameters a bit clearer. Maybe like explain a bit clearer, more clearly what this construction is doing. Okay, so the key idea here is that this notation is defined in such a way that you build sets where if you can lower bound the communication complexity of the set, and what I mean by that is you have a set of matrices, and the communication complexity of the set is the communication complexity of the matrix with lowest communication complexity in that set. So if you can lower bound that, you the sets are defined in such a way that like we can use that bound to inductively say something about basically larger set, or that's where the parameters of the bracket notation, the p parameter has increased, and all the other parameters have also been modified. So we can basically relate the complexity of these different sets, which will be useful in in lower bounding the overall complexity of the construction, and not just lower bounding, but actually making statements about the behavior of optimal protocols. So just to sort of illustrate a bit what the bracket notation is doing, here are some simple examples. So if you have a matrix A interlaced twice, so our basic matrix 1, 0 interlaced twice, and you set the Y parameter to 3/4. So basically what this is saying is like you're keeping 3/4 of the columns, so 3 columns in this case. If you didn't fall on an integer number, you take the ceiling, by the way. But so in this case, you take 3 columns. So the set built in such a manner is, so first parameter 2 is basically saying we interlace A twice. And because the X parameter is 1, is basically you take all when you're interlacing, you're taking all the rows of A when you interlace it twice, and then you keep 3/4 of a column. So you end up with these 4 matrices, which are all possible combinations of a columns. So to illustrate what the second parameter is doing, if you set X to half, and you have a matrix, 2 by 2 matrix this time that you're interlacing, X means when you're going to build the set that you interlace, you only take half of the rows. So in this case, just 1 out of the 2. So if we interlace I twice, you end up with this matrix. So it's duplicating each column, because there's 2 columns in this matrix. So you duplicate the first column twice, concatenate a copy of the matrix, duplicate the second column twice, concatenate a copy of the matrix here. But so for the bracket notation, because the parameter X is a half, we're not interlacing I with itself. What we're interlacing is the set where you take only half of the rows. So so that means you pick one of the 2 rows here. So you either end up with the top row or the bottom row, and you're interlacing that set twice, which actually gives you 4 matrices, because so you have the first matrix here, which is we took the top row in both copies of I that we're interlacing, or in both sets that we're interlacing, and so you end up with 1 0, where so 1 1 duplicated twice, and you append 1 0, and then 0, like duplicating the 0 twice and appending 1 0 here. This matrix here is when you interlace the elements of a set where the first one is you took the second row, and then the second set you took you're interlacing with a matrix where you took the first row. So you end up with duplicating 0 twice, then 1 twice here, and appending the first row. This is the other way around, and this is the final one where you took both bottom rows. So duplicating the 0 and appending 0, 1, and duplicating the 1 and appending 0, 1. Now, if the third parameter here were not 1 but say 3/4, what you would end up with is for each one of these matrices, you would end up taking 3 of the columns, and so if you go from this matrix, you would build a three matrices, and from this one, 4 matrices, and then from this one 4 new matrices, and again, and same for each one of these. So end up with 16, a new set with 16 matrices. Some might collapse, yeah, like for example, if you delete the 0, like if you the matrix where you take this one, and this one is the same as the one where you take this one, and this one, so you wouldn't actually end up with 16 matrices, but so you'd end up with a new set of matrices built in that manner. So this is what the bracket notation is doing, and so hopefully this kind of gives you this example gives you a better sense of that. And it is built in such a way that we can trace what the protocol is doing on these sets of matrices. So here we have what we call the partition lemma, and it's basically what allows us to relate larger games to smaller games. The idea is here you can see that on the right hand side you have a bracket notation, and actually let's look at the second line. You have the bracket notation here, and you have a statement about the complexity of P interlaced games, and so there's this 1 minus tau here that's a subtlety, but let's focus on this one here, where basically you have around P interlaced games, and what you can say something about the complexity of the bracket notation where you have 2P interlaced games, and the thing to observe is that the number of columns that you have to keep goes down exponentially fast. You have this term in the exponent here, and this basically says that, like, as we interlace more and more games, the number of games you're interlacing goes up exponentially, but so the number of columns that you have to keep also goes down exponentially, basically. And so we can do an induction over this, like k times, which gives us one round of our alternating communication game, where you can basically we end up with a statement where we say that we can eliminate some exponentially large number of columns and yet still remain with keep the same complexity. And so to get this partition lemma, basically we use the properties of the construction. It's a highly symmetric construction, and so there's some basically structural lemmas that allow us to relate the sets that are in this interlaced 2p times to the sets that are interlaced p times, and the 3 lemmas that I used to do so are the balancing lemma, and 2 projection lemmas. So I'm not going to go into the details of the balancing lemma because I think, like, it's not conceptually it's not the most important one, but the projection lemmas are important and fairly simple. So, like, I'll explain the idea behind those, and
And hopefully this gives a sense of how we're doing this. So imagine that you have this is basically some arbitrary matrix with it could so the blue color, green color, and yellow color can basically represent submatrices. Um, Typically, in the way we're using the interlacing operation here, what you would represent by a different color every index of the columns, but you can have this be a vector basically. So like you can have as many rows as you like, and but just one column. So the blue part of this the blue cell here would be a vector basically with an arbitrary number of rows in one column, and so here you'd have like three column matrix, and when you let's say you interlace it three times with itself, and so you end up with something like this, where you can see that um, you've basically duplicated the blue cell nine times because you interlace it um, uh, with uh, with itself twice. And so if we have this interlaced matrix where we interlaced our base matrix three times, and if you emit 2 bits, which corresponds to keeping 1/4 of the columns, so 2 bits emitted, like the column player emits 2 bits, you can find one of the elements of the partition. The largest element of a partition will have at least 1/4 of the columns. So an example of such an element could be this matrix where basically you've kept this is like, so you're left with 7 columns, which is going to be um, uh, a quarter of 27 basically. Take the ceiling, and what the lemma that we're using, we want to relate this to um, to the interlace operation where we've done less, basically we've interlaced fewer times. So here we've interlaced three times the base matrix, and I want to relate this set of matrices that I obtained by keeping a quarter of the columns to a set of matrices that I would obtain after interlacing two times. And so to think, the way we were thinking about this is, um, because the interlace operation is highly symmetric, you end up with every possible string, every possible sort of combination of three colors here. Uh, you can kind of think as it as a, like if you interlace three times, it's a three-dimensional lattice where every possible column corresponds to a location on the lattice. So you have like here this I guess hypercube that we discretize, and every column corresponds to one of the smaller cubes in the hypercube. And so when here I've basically colored in the 7 columns that are remaining in the element of a partition in a hypercube. So you can have a look for yourself. Like uh, the one that's all blue would correspond to coordinate 0 in the x direction, in the y direction, and in the y direction. So this is the one at the back here. Uh, Now this one, which is 0, 0, and 1 in the z direction, is the one on top of it that you can see here. Here you have 0, 3, and 1. So that would be like, so 0 in the x direction, uh, 3 in the y direction, and 1 in the z direction. So it would be this one, and so on and so forth. Um, so now the observation that we used is, so it's a sort of I guess we were thinking about it geometrically, but it's a combinatorial lemma that the idea is that like if you project on one of the faces of this cube the the subcubes or the small cubes, if you have a certain like um, amount of the area that's colored in, the if you project onto the faces, the ratio is going to go up exponential, or is going to you're going to get a like larger ratio of the area being colored in. So you can see this here, where so if you take the max, like you project onto all the faces. So or well, all the directions. So the X, Y, YZ, and XZ directions. Um, if you take the sort of one which has most area covered, you can basically lower bound the area covered in terms of a ratio or of the area that's covered in the cube. And so if we translate back to our game or to our matrix here, when we have only a fraction of a columns remaining, if we project our interlaced game, so basically by that I mean if we like here if we get rid of the middle row and we end up with this object, and if we look at like what it looks like when we only keep the remaining columns, so it looks like this. So basically you've just eliminated the middle part of the tuples, and we want to relate that to what does that look like in terms of the interlaced matrix where we've only interlaced the base matrix twice and deleted columns. So these columns are going to be found in that matrix. So here we have this thing, which is the columns that have been kept, and we've deleted the middle row. And this is the game you would obtain, the matrix you would obtain by interlacing twice the base matrix. And if you look for these columns, where are they found in the matrix which is interlaced twice? Basically, it looks like this. So you can see that like you have a much larger ratio of the columns that is remaining in the matrix that's been interlaced twice. So hopefully this sort of gives you visually what the idea is, how we basically prove that as this construction grows bigger, even if you delete many columns, you can sort of relate. You're not affecting the complexity basically, because you can use these structural lemmas to show that like you're not having a large impact, because you can find in these large matrices like interlaced many times where you've deleted lots of columns, you can find sub games or sub matrices that are smaller but that like have very few of the columns remain, like have lots of the columns remaining basically. Um, so okay, so uh, hopefully this gives a sense of how these combinatorial lemmas help us sort of prove the lower bound for the construction. The key idea is that once you have these structural lemmas, you can sort of analyze one step of um, basically one step of what the protocol can do, and show that like no matter which player emits a bit, you can find one of these submatrices um, which has high complexity, using these structural lemmas to sort of relate the the elements of like the partition on the larger matrix to something using the like the bracket notation for like smaller construction where we've already shown a complexity bound. So you can basically inductively um, uh, sort of prove the complexity for larger and larger element or larger and larger functions in the family of functions. Um, and as I was saying at the beginning, I like there's the technique in itself, like this interlace operation, I think is very generic, and there's variants of it that you can define. So here, like you can see that like as you increase the number of rows, you get something exponentially large. That's not strictly necessary to get the desirable properties of construction. You could actually build a version of this interlace operation where the matrix remains polynomial in size in terms of like number of interlace operations that you're are doing, and so and still like use the similar structural lemmas to actually show something about the complexity of the construction. So I think it's a interesting family of functions that have like you can sort of tweak them to have desirable properties, but where the nature of the construction allows us to show complexity lower bound in a way that's not doable with traditional methods. And actually, we show in the paper that the complexity bound that we obtain using these techniques is not obtainable via via rank methods or monochromatic rectangles, full length sets, or discrepancy. Yeah. So I guess yeah. In terms of moving forward, the uh, the I guess one immediate question that we're addressing and most likely going to include in the journal version is um, it's possible to adapt the construction just to resolve the sort of two function version of a question. So here the idea is like, if you have any arbitrary function f and g, how does the complexity of taking them together relate to the complexity of taking them separately? And I think without changing the construction that much, you can show that you can find a function f such that for any function g satisfying certain conditions, the complexity of f and g is actually just the complexity of f. So that's a statement that we're sort of working on for a journal version. I think maybe more interestingly, like I was saying, we actually know how to build a construction that behaves in a similar manner that's polynomial in size, and that can be adapted to other problems in communication complexity, where the sort of size of a matrix is you have to be more careful. Um, I think also, yeah, we want to think about variants that have where you sort of like um, uh, want to be more careful about the properties that the construction has while still preserving this the the structural components that allow you to to prove a lower bound in this fashion. Also, I guess, yeah, like thinking about a sort of version for multi-party communication complexity. And yeah, so I guess that's it. If you have any questions, feel free to email me. This is my email address. And also, if you're attending STOC, I'll be there and give a live version of the talk. Thank you.